Welcome to Section 1, Lesson 6. Today we look at scientific notation, the universal way scientists, engineers, and computers write very large and very small numbers without losing track of digits. By the end of the lesson, you will know exactly how to convert any decimal number into scientific notation, how to convert it back, and how to multiply and divide numbers in this form using the exponent rules from the previous two lessons. Scientific notation will quickly become the most useful single piece of compact notation in your entire algebra toolkit, and you will use it constantly through the remaining sections of the course, especially when we get to exponential and logarithmic functions in Section 13, where the entire conversation revolves around the magnitude of numbers across many orders of magnitude. First idea on the board. One notation called scientific notation handles both huge numbers and tiny numbers without ambiguity. The mass of the sun in kilograms has 30 digits in front of the decimal. The wavelength of visible light in meters has 6 zeros after the decimal point before the first non-zero digit. Both can be written cleanly as one digit, a small coefficient, times the power of 10, with no need to count or write all the zeros yourself. Second idea, the format is always the same. A coefficient whose absolute value is at least 1 and strictly less than 10 multiplied by 10 raised to an integer power. So 3.14 times 10 to the 8th is valid, but 31.4 times 10 to the 7th is not, even though the two expressions equal the same number. The strict range on the coefficient is what makes scientific notation a unique representation, so any two scientists writing the same number in this form will write it identically. Multiplying and dividing large or small numbers in scientific notation reduces to two simple operations. Multiply or divide the coefficients normally, then add the exponents for multiplication or spurt them for division, exactly as the product and quotient rules from the previous lessons taught us. The exponent rules from lessons 4 and 5 do all the heavy lifting in scientific notation arithmetic, which is why those lessons came first. Here is the formal definition of scientific notation. A number is in scientific notation when it is written as a coefficient multiplied by 10 raised to an integer power n. The coefficient must satisfy 1 less than or equal to the absolute value of a less than 10. The exponent n is any integer, positive, negative, or 0. The coefficient is the leading digit, followed by however many decimal digits the precision demands. Take the number 602,000 billion. That is 23 zeros after the leading 6 and the 0 and the 2. Written out longhand, it is unreadable. Written in scientific notation, it is 6.02 times 10 to the 23rd. This number is Avogadro's number, the count of atoms in 12 grams of carbon. The exponent 23 is the count of decimal places. We shifted the original decimal point to the left. Now take a tiny number. The charge of a single electron in coulombs is 0.000000000000000016, 18 zeros after the decimal before the leading one. In scientific notation, that is 1.6 times 10 to the negative 19. The negative sign on the exponent counts how many decimal places we shifted the original decimal point to the right. The negative exponent rule from the previous lesson is what makes this representation work for tiny numbers. Here is the procedure for large numbers. Take a number like 40, 7,300,000. Find the position where the decimal would go to leave a single digit before it, in this case between the 4 and the 7. The number of places you shifted the decimal to the left is the exponent. 47,300,000 becomes 4.73 times 10 to the 7th because we shifted 7 places to the left. Here is the procedure for small numbers. Take 0.00052, shift the decimal to the right until the leading digit is a single non-zero number, in this case the 5. We shifted 4 places to the right. The exponent is the negative of that count, so negative 4. The number becomes 5.2 times 10 to the negative 4. Same procedure as before, but the negative sign on the exponent records the rightward shift. Multiplying two numbers written in scientific notation is one line of arithmetic. The product of a times 10 to the m with b times 10 to the n equals the product of the coefficients a times b multiplied by 10 raised to the sum of the exponents m plus n. The product rule from lesson 4 does the work on the powers of 10, and the coefficients multiply normally. The same template works for division with subtraction in place of addition. Here is our first worked example, converting a large number into scientific notation. The number at the top is 47,300,000. We need to identify the coefficient, identify the exponent, and combine them into the standard scientific notation form. Step 1. Decide where the decimal needs to go so the leading digit stands alone. The original number has its implicit decimal point at the very far right, after all the zeros. To bring the decimal up between the 4 and the 7, we shift it 7 places to the left through the digits 7, 3, 0, 0, 0, 0. Step 2. Read off the coefficient. After the decimal shift, the digits in front are 4, 7, 3, so the coefficient is 4.73. This satisfies 1 less than or equal to the absolute value less than 10, exactly as the definition requires. We drop trailing zeros that are no longer significant. Step 3. Read off the exponent. We shifted the decimal 7 places to the left, so the exponent is plus 7. Leftward shifts give positive exponents, rightward shifts give negative exponents. Step 4. Combine into scientific notation form. 47,300,000 equals 4.73 times 10 to the 7th. The two expressions evaluate to the same number, but the second is far easier to multiply, divide, or compare against other large numbers. So the answer in scientific notation is 4.73 times 10 to the 7th. The big takeaway from this example is that the conversion is mechanical. Count the decimal shift to land between the leading digit and the next, then sign the exponent according to the direction you shifted. Always practice the conversion until it becomes a reflex, because nearly every science formula expects inputs already in this form. A useful sanity check after every conversion is to read the scientific notation answer back as a magnitude. 4.73 times 10 to the 7th is between 10 million and 100 million, which matches the original 47 million we started with. If your converted form ever lands a power of 10 away from the original magnitude, you miscounted the decimal shift. Here is the second worked example, multiplying two numbers that are already in scientific notation. The expression at the top is open parenthesis 3 times 10 to the 4th, close parenthesis, multiplied by open parenthesis 2 times 10 to the negative 7, close parenthesis. The coefficients are 3 and 2, the exponents are 4 and minus 7. Step 1. Group the coefficients together and the powers of 10 together. Multiplication is associative and commutative, so we can rearrange. The expression becomes the quantity 3 times 2 multiplied by the quantity 10 to the 4th times 10 to the negative 7. Step 2. Multiply the coefficients. 3 times 2 equals 6. The expression now reads 6 multiplied by 10 to the 4th times 10 to the negative 7. Step 3. Apply the product rule from lesson 4 to the powers of 10. The product rule says add the exponents when multiplying powers of the same base. The base is 10 in both terms, so we add the exponents 4 and negative 7. Step 4. 4 plus negative 7 equals negative 3. So the entire expression simplifies cleanly to 6 times 10 to the negative 3. So the final answer is 6 times 10 to the negative 3. The big takeaway from this example is the two-step pattern for multiplying any two numbers in scientific notation. Multiply the coefficients normally, add the exponents on the powers of 10. The same procedure works for any number of factors, and the same template with subtraction in place of addition works for division. A quick sanity check on this answer: 6 times 10 to the negative 3 is 6 thousandths, or 0.006. The original was 30,000 times 0.0000002, which a calculator confirms equals 0.006. The scientific notation result matches the literal arithmetic exactly as it should. Notice how the negative exponent in the answer was not something we had to think about as a separate case. The exponent rule simply added the original 4 and the original negative 7, and produced negative 3 as the result. The mechanics of the product rule handle positive and negative exponents identically, which is part of what makes scientific notation so robust. 3 mistakes that catch every student when they first work with scientific notation. Each one comes from a small bookkeeping slip in either the direction of the decimal shift or the range of the coefficient. We go through them in turn. First mistake. A student writes 0.0007 equals 7 times 10 to the fourth, picking the wrong sign for the exponent. The original number is small, less than 1, which means we shifted the decimal to the right GHT to extract the leading digit. Right shifts make the exponent negative. The correct answer is 7 times 10 to the negative 4. Always sign the exponent by direction: left shift positive, right shift negative. Second mistake. A student writes a number like 31.4 times 10 to the 7th with a coefficient that is too large to be in scientific notation. The coefficient must satisfy 1 less than or equal to the absolute value less than 10. 31.4 does not. The correct form is 3.14 times 10 to the 8th. We had to shift the decimal one more place left in the coefficient and bump the exponent up by 1 to compensate. Third mistake. A student writes 4,730,000 and reads it as 4.73 times 10 to the 6th, when the correct answer is 4.73 times 10 to the 7th. The shift count was off by 1. Always count the decimal shifts carefully by hand the first few times until you build a feel for the right exponent at a glance. Scientific notation is everywhere in the technical world. The 4 examples here are the ones you will run into most often in chemistry, physics, computer science, and astronomy. Each one would be unusable in standard decimal form, and each is trivial to read once you accept the scientific notation convention. Avogadro's number, 6.022 times 10 to the 23rd, the count of atoms in 1 mole of any substance. Every chemistry calculation that converts between mass and atom count goes through this constant. Written out longhand, it would take 24 digits, which is unreadable. In scientific notation, it fits in a single line and lets you multiply or divide by it without losing track of decimals. Electron charge, 1.602 times 10 to the negative 19 coulombs per electron. Every physics formula that connects voltage, current, and the count of charged particles uses this constant. The negative 19th power makes it tiny by everyday standards, but each individual electron only carries that much charge. Computer floating point format. Every double precision floating point number stored in a computer's memory is internally a coefficient times 2 raised to an integer exponent, almost exactly the same idea as decimal scientific notation, but in base 2. This format lets a single 64-bit slot represent numbers from atomic size up to galactic size with about 15 significant digits of precision. Astronomy distances. The distance from the Earth to the Sun is about 1.496 times 10 to the 11th meters. The diameter of the Milky Way galaxy is about 9.5 times 10 to the 20th meters. Astronomers compare such different scales daily and would never bother writing them in standard form. Scientific notation is the only practical way to do astronomy on paper. 3 things to take with you from this lesson. Scientific notation is one of the most useful pieces of compact notation in all of applied mathematics and the rules are short enough to internalize in a single sitting. First, the format is always the same. A coefficient whose absolute value is at least 1 and strictly less than 10 multiplied by 10 raised to an integer power. Memorize the range on the coefficient because that constraint is what makes the representation unique and what catches the most common error. Second, the sign of the exponent records the direction the decimal point shifted. Shifting left, which happens for large numbers, gives a positive exponent. Shifting right, which happens for small numbers, gives a negative exponent. Always sign the exponent by direction, not by guessing. The single most common error in scientific notation work is a sign flip on the exponent, so build the habit of asking yourself which direction you shifted the decimal before writing the answer down. Third, to multiply two numbers in scientific notation, multiply the coefficients normally and add the exponents on the powers of 10. To divide the coefficients and subtract the exponents. Both rules come directly from the product and quotient rules in the previous two lessons, which is why those lessons came first. Once you internalize the format and the two arithmetic moves, multiplying and dividing astronomically large or microscopically small numbers becomes as easy as multiplying single-digit numbers. The big productivity win is that scientific notation lets you work entirely with single-digit coefficients, and all the magnitude bookkeeping happens on the exponents alone. So a chemistry problem that requires multiplying Avogadro's number by an electron charge does not require manipulating 23-digit numbers. It only requires multiplying 6.02 by 1.6 and adding the exponents 23 and minus 19. The product is 6.02 times 1.6, which is roughly 9.6 multiplied by 10 to the fourth, or about 96,000. The whole calculation fits in 2 lines and requires no calculator. Coming up next, the lesson called Estimation and Reasonableness, where scientific notation will be the first tool we reach for to sanity, check answers in physics and chemistry problems before relying on a calculator's output, and where the round and check habit will save you from countless silent calculator errors.